G'day, mates. This is Hao Mack Yang, and I'm going to be your tour guide for Quantum Odyssey, the educational game for quantum computing. Today, even though it's April Fool's, I will be announcing that I will be hosting a weekly session video series in the style of Khan Academy in preparation of World Quantum Day, which will be celebrated on the 14th of April every year since 2021. Quantum computing, and in fact, quantum, even the word quantum, has a reputation of being difficult and weird. But by watching this video series, you will be able to understand how this game works and how this game connects to the notion of quantum computing and more broadly, the mathematics behind that, such as linear algebra and how this applies to the real world. So make some connections between the game, quantum mechanics, mathematics, and everyday life. But as always, the theme of this video series is about this game itself. Mostly about this game, because ever since its relatively long development time of 6 years and its early access release in the end of January 2025, I will be hosting you to get new players on board with this exciting puzzle and then connect this puzzle with the notion of quantum computing and the mathematics behind that. So first of all, you might have seen these symbols. These symbols over there are the design elements of Quantum Odyssey. There is a story mode and there is a community-led challenge mode. The story mode called Descent. Convergence is the other mode, which has been renamed Descent. This Descent mode pits the player against various tutorials and preset puzzles, starting from the inner ring all the way out to the outer ring. The challenges become more difficult as you move from the inner ring to the outer ring, and two of the challenges since the release has been proven to be considerably difficult, which the game affectfully calls it impossible. Over there, the four dots, the four circles represent the sigil colors. The sigil is just Quantum Odyssey's way of saying a qubit, or more accurately, the component of a qubit along one of its measurement outcomes, or in more fancy words, eigenstates. The lines over on the right represents the gates and how they are visualized in Quantum Odyssey. This way, it allows players, quantum enthusiasts, and quantum software developers to better visualize how each gate acts against a qubit, which could be represented by multiple sigils lining on lanes. Let's go with a quick introduction to what is the basics. So, what is quantum? So, in pop culture, in layman's terms, quantum has a very fearsome reputation. What is quantum? Actually, the word quantum actually doesn't even come from this physical phenomena. But quantum, the word, quantum means amount. Of, or base amount. Moreover, this term is used in the legal language. But because the word quantum is so closely associated with the notion of quantum mechanics, unless you're a lawyer or work in the law field, you might think of quantum as this weird phenomena between two particles, causing them to act as an indivisible whole, no matter how far they are separated. The future of computing, which allows algorithms to be sped up exponentially, making otherwise intractable problems tractable, or Einstein, Dirac, all these weird equations, like the very famous Schrodinger's equation. Schrodinger's equation is nothing more than a differential equation, which itself is something universally level. That just says the imaginary Planck, reduced Planck derivative of the state that can be thought of as a function is just a state undergoing an easily described transformation that satisfies properties such that it is familiar in the real world. Like field axioms, which is nothing more than just high school or middle school algebraic laws, like associativity, commutativity, identity, and inverse and distributivity. This equation in blue is a Schrodinger's equation. Quantum mechanics is the mechanics that deals with the very small, to the point that it becomes indivisible like an atom, and it is highly tied to probability. Quantum mechanics allow particles to assume an intermediate state, a probabilistic intermediate state. For example, a ket, which we can often just call it a ket. So like state off means 0, state 1, which means on. But a particle can also be in an intermediate state, which has this odd expression, 0 plus 1 root 2, which in sigil terms, 0 is nothing more than a sigil on the left with a full size. 1 is nothing more than a sigil on the right. And the sum over the root 2 is just nothing more than two half-size sigils in terms of area on both sides. It's like splitting a pie that is of size 1 and the radius, 1 radius, to turning into two pies with half the area. Nothing more than that. But if you measure a qubit in this intermediate state, this is where the word quantum comes into play. You have half a chance of observing the quantum bit in the on state and a 50-50 chance that you will see the qubit in the off state. Because ultimately, the result is always a whole number. So quantum is also associated with the word whole number. We will discuss more about quantum mechanics further along as we move to the outer rings of the descent. Now we will work with the rules of the game. So the rules of this game, it's ultimately nothing more than a puzzle game. So Quantum Odyssey is an online. In fact, we don't even need to call it an online, is an interactive puzzle game. With the intent of teaching players how to explore and master quantum computing. So that is all. However, ever since its launch, it has been reputed as a difficult game. Much like how magnum opus is a way to teach players how to compute or implement a computer using hexagonal tools. Quantum mechanics. However, it is more like connecting wires and colors. So the Sigil, which is a ball, combinations match the bottom configuration. So it's like that, nothing more like that, nothing more than this. For example, let's say seagulls come from the top, which is also predetermined depending on the game mode and the particular puzzle you want. And then you have to use various tools to bring this sigil to that configuration. Let's say over there using the available circuit elements. However, there are limitations in how you can place the connectors, like gates. For example, when you select an X gate, you have to apply X gates on all of the pairs that are being affected, like this. And then do the H gate, you will then have to transform it again, with all the applicable pairs that's being found. You cannot just apply an X gate on just arbitrarily one pair of lengths. So you cannot simply do that. So you cannot simply do that in one gate. So here's the thing. Cannot just apply an X on one side. The gates are also labeled by a binary string, which can be interpreted as a single number. In this case, that will be a 2-qubit system. So there are 4 possibilities, namely labeled from 0, 0, 0, 1, 0, 2. No, it's not 0, 2, but it's 1, 0, which can be interpreted as 2, and 1, 1, which is 3. You apply an X gate on the 0th slot. That means the rightmost slot, the least significant slot, place value. Firstly, that means the number of pairs affected would be 2. There are 2 pairs affected. They're identified by the bits not affected. In this case, it's 0x and then the 1x thing, which that x just represents the bit being affected. But you have to apply to all of the applicable pairs. That's organized in this way. You cannot simply try to switch and make this length using a single X gate. In fact, you'll have to use 3 X gates to implement that. In fact, that's called a controlled NOT gate. That's actually 2 of them. 2 gates, but I can also say it's 3 because we can see C as also a gate. So this is an X gate applied on the 0th row. While the first row remains untouched. So this is the thing. The Sigil would then flow from the 0, 0 slot to the 1, 1 slot. But unfortunately, this does not match this combination down there. Then what is a sigil? The next element is, what is a sigil? Or sigil, or whatever I could say. So an element. The sigil. The Sigil the Sigil is a ball, a colored ball that rolls, or better to say, a colored disc that rolls from the top to the bottom. A sigil has a color or two and a radius. And in quantum mechanics, a qubit is an arrangement of sigils that means in Quantum Odyssey terms, such that the area of all the sigils so the total area of the sigils equate to pi. For example, when a qubit is in the zero state, for example, it corresponds to a sigil of size 1 on the leftmost. Likewise, a 2-qubit system in the 0, 0 state is represented as a single qubit of size 1 on the leftmost node, leftmost lane. Likewise, we have the minus state. The minus state, which is equal to 0 minus 1 over root 2, can be seen as two half-sized sigils. Two half-sized sigils. The left sigil, which is on the 0 lane, has a radius of root half, while the right lane over there, the radius is also root half, which is approximately 0.71. Sigil colors. Sigil colors and sizes. So in a normalized ket or qubit, in Quantum Odyssey terms, the size of all the disks must sum up to pi. That means it's a disk of radius 1. So sigil positions sizes, sigil positions correspond to outcome kets, to outcomes, which are represented as kets. Informally, sigil colors correspond to phases or signs, which is this. Plus, minus, the imaginary unit, and negative imaginary. So 4 colors. And of course, if you have taken complex analysis or even have like a grasp of how complex numbers are used, imaginary numbers are used to visualize rotation, which the imaginary unit represents a quarter turn. Imaginary units are also used to express rotations in a compact way, namely through the exponential function and Euler's formula. Finally, sigil radii, which is shown in Quantum Odyssey, corresponds to coefficients and multipliers. Sigil area, which is squared radii, proportionally corresponds to measurement probability. So we have some examples of sigils, or like whatever I would like to pronounce. Let's say this is the sigil in the default position. A blue sigil, that means positive, unsigned, going forward of radius 1, the 0 state. Let's do it in a 4-qubit way. While the others are absent. Likewise, we could split the sigils into 4 cardinal directions, namely the sigils of a solid color. These sigils would have radius a half, so their value shown as a half. This sigil represents the value. Half of 0, 0 plus half I 0, 1 plus minus half of 0, 1, 0 minus I of 1, 1. We can change the colors just to better highlight. The rows, so half, half, but ultimately it really means quarter. Half and half. Over there. Likewise, a sigil can also have some other amplitudes that can point diagonally as well. For example, a sigil, we have two sigils that actually compose of two colors, namely blue-green and blue-yellow. Blue-yellow. In this case, the total area, however, sums to 1 again. But it can be seen as you have 4 of these, but you mix them together to form a bigger composite qubit. This case, this expression would be that the 0 state would have an amplitude of half plus I half in the first state, namely state 0, plus its conjugate number pointing directly downwards on the complex plane. But ultimately, the area is still half of pi. So just take a few minutes of break for me to identify how sigils work. Okay. Okay, let's move on. So after all of these instructions and stuff, we will move on to the next element. The other element in Quantum Odyssey is the wire. Or laying, or something. The element is the wire. So quantum wires, again, behave very differently from classical wires. And the qubits or sigils you transformed, gates are used to split sigils and these stuff so that it matches the bottom. The wire and its many crossings represent the path the sigils take and the quantum gates attached to it. Like sigils, wires also have a color and a thickness. This corresponds to complex multiplication. This corresponds to complex multiplication. The most basic familiar wires are these. The most basic wire, which we have to include it for completeness, is the identity wire. The identity wire does nothing to the qubit or sigil. A blue sigil would remain blue when passing through the straight line or the ice gate, and a red qubit will remain red. A yin-yang qubit, which is one whose face is diagonal, will remain the yin-yang in the same direction. And an eye, which is all the qubits which are in any other direction, will remain in the eye in the same color distribution. This is the eye gate. And it means the operation, the gate that does nothing. It remains, means leave the gate alone, unchange the gate, that thing. The gate which I have already introduced to you unofficially, and it's probably the most familiar, the one that most quantum enthusiasts would first learn, is the X gate. The X gate switches the positions of two sigils based on the particular bit that identifies the sigil. So it's better to just write it down like this and hide all the other irrelevant lanes in a multi-lane system. So any qubit, any pair of qubits which differ only by one bit, which is a selected bit, sigil would have their position swapped. We have the Y gate, which is the least familiar of the XYZ poly gates. Also swaps the positions, but it also changes their amplitudes as well. So a sigil who's on a lane that's being affected by a Y gate and whose affected bit is 0 would also have their face turned 90 degrees counterclockwise. No matter why the white gate is being taught last in Quantum Odyssey. The Z gate does not swap sigils, but it changes the color of the sigil. Namely, it negates the color. That means reverses the color of the sigil if the affected bit position's value is 1. And the last of the big familiar ones, which you should definitely know, is the Hadamard gate. The Hadamard gate is the gate that splits or merges the sigils, depending on their colors and their sizes. This is where addition comes into play. The bits, the thickness of the wires in a Hadamard crossing is narrower. Namely, the cross section would be only half as large as that of the X, Y, and Z gates. And moreover, the rightmost branch of the Hadamard gate is red. It cannot be blue because in the classical, that is part of the reason why there's the quantum weirdness effects comes into play. So the Hadamard gate causes a blue sigil on a lane whose affected bit is at the value of 0 to be split into two smaller sigils of equal size. So we have R would go under a Hadamard gate transformation, and it will be split into two half-sized disks, each of radius 0.71 r. On the positions cat 0, cat x0x, and then cat x1x, which the x's are just sequences of ignored bits. It is like flipping a coin. You apply the Hadamard gate to cause a coin landing on tails, the 0 state, to be a coin that's up in the air with a 50-50 chance it will land on heads or tails. But in the classical formulation, you might be tempted, if you try to do that again, it will still be 50-50. But in the quantum case, no, this is not the same. The reason is although like coin landing on the one position, so heads, tails, heads positions. If you flip that as well, you will also get like a 50-50 split. But here is a problem. Here's the difference. The part of the lane, part of this sigil that remains of the same lane, gets its sign flipped to negative. So you have this thing over there. So that diagram corresponds to, hey, I am tossing a coin that is in heads, in tails, up in the air. This is when, hey, I'm going to toss a coin that's landing on heads, tails, heads, up in the air as well. So 50-50. But now you want to like do this again. You want to do this again. So 0.71. So let's say you have this configuration, 0.71. So two smaller half-size sigils with radius 0.71 and 0.71. Okay, this thing would be flipped into 0.5, so quarter size, 0.5, but now the state one slot will get a negative 0.5. And when two sigils combine, that's addition. That's when addition is being performed. And there's another level of weirdness. Addition, actually, this thing, you're adding radii into the thing. So suddenly, the size of the qubit suddenly quadruples, doubles, makes it double than intended. So this is another part that makes quantum mechanics weird. You're adding the radii when you are performing sigil addition. But if you're splitting the sigils, dividing the sigils, or putting a sigil on a lane other than blue, then you are multiplying the sigils. For example, a blue line corresponds to multiply by 1. A red line means you multiply it by -1. Likewise, a green sigil means you multiply it by I. And so on, so on. You might see like wires that are two colors as well. These are wires which rotate the face of a qubit by any angle that is other than 90 degrees or 180 degrees. For example, in a T-gate, the right lane, the lane whose status is 1, this thing multiplies the qubit by by the fourth root of -1, which you can also see it as the root I. You can also write it as e to the quarter pi I, or like a 45-degree anti-clockwise rotation. But nevertheless, in rectangular coordinates, we have, of course, 1 plus I over root 2. 1 plus I over root 2. So you can see it on a complex plane. So 0, t, 1, and t of 1, like that. And then it's nothing more than I over root 2, 1 over root 2. 1. Nothing more than that. But nevertheless, you can like try to like view this thing cross-sectionally, and you will see that this is a wire of radius 1, whose color distribution is half blue and half green. It is only when you are merging the wires together like that is where we are adding A plus B plus gamma, which we will assume the lanes have thickness alpha, beta, and gamma. This is the part that addition of sigils is not intuitive. For example, in the Hadamard case, we have two quarter-sized qubits add together into a full-sized qubit. But that doesn't make sense. Actually, it doesn't make sense because classically, because when you merge two quarter-sized qubits of radius half, you get a half-sized qubit of radius a quarter, which is what happens when you split a qubit. Like that. Like, hey, like you split a qubit. For example, in the Hadamard case, we have 1 is equal to 0.7 1/2 plus 0.7 1/2. But now there we have 0.5 plus 0.5 is equal to 1. So splitting, you are splitting just the square. You are just splitting and then returning the radius. But when you're adding, you're actually adding directly the radius and not the area. This is where the counterintuition comes from. When you are splitting, when the wires split, that means their areas have to sum up to the original. But when they merge, their radius has to some to the original. This is another evidence of quantum weirdness. So in this very first hour, I have demonstrated everything about the basics of Quantum Odyssey and how this connects to quantum mechanics without diving deep into what is a ket, first of all, what is quantum mechanics, but just the mechanics of the game. Eventually, you will learn linear algebra and the academic parts after progressing considerably through the game, and you will be tasked to connect these complex numbers, linear algebra, and functions involved in quantum computing and how this relates to the game. So, as always, I will post these on YouTube every week, even though I will be very busy for the next few weeks. I will have a special episode for you this Easter, and we will become great Quantum Odyssey checkers. See ya.